Now, sound waves are still waves, so everything that I talked about for interference is still going to apply. Remember, if I had a string instrument and if I plucked it and set up a standing wave like that, and now I want to go ahead and have that wave be reflected, so now I'm looking at that and this wave has now been reflected in the backwards direction. If I add those two waves together, then I'm going to get no wave. I'm going to get this thing that I call destructive interference. Similarly, if I have my guitar string and I have a wave like that, and I take my guitar string and I have another wave with some amplitude of like that, and I add these two waves together, I'm going to get a big large amplitude. So I'm going to have constructive interference over here, and I'm going to have destructive interference over here. If I look at sound waves, I'm going to have the same type of thing. I'm going to have these crests, these wavefront crests moving out from my speaker as such, and I'm going to have the same thing for this one. I'm going to have my wavefront crests moving outwards right there. My troughs are going to be in the middle right there. Same with this one right here. And I can have points such as this point right here labeled C, where I'm going to add my two crests together. So I'm going to have this thing called constructive interference right there. I'm also going to have points like point D, where one of the waves is at the crest and the other wave is at the trough, and effectively they're going to cancel each other out. We're going to have destructive interference right there. So we're going to hear a lot of sound right here. It's going to be a large amplitude. However, we're also going to have points right here, like point D, where we're not going to hear any sound. Sound waves can also interfere in time, causing this interesting phenomenon called beats. Musicians are excellent at being able to hear these beats. I'll be honest with you, I cannot hear them. I am musically tone deaf. What we're looking at for beats is we're going to be looking at two frequencies that are being played. Let's just say a 50 Hertz frequency, which is going to be this blue curve right here. And we're going to have a second frequency that's going to be at 60 Hertz, that's the red curve. And if we look at these in terms of time, let's just say that they both start out at their maximum amplitude. Now this 50 Hertz guy is going to oscillate back and forth quite a bit faster than the 60 Hertz frequency, and we can see at some points they're going to both have a large positive amplitude. We're going to have points where one of them has a crest and one of them has a trough, and then we're going to have points where they line up again. And if we think about it, we just more or less add these two frequencies together in terms of their amplitude. They're going to constructively interfere here, they're going to destructively interfere here, and they're going to constructively interfere here. So if I look at my loudness, I'm going to have a very loud sound right here, and then about half a second later I'm going to essentially have no sound. They're going to constructively or destructively interfere in time. Then I'm going to have a loud sound right here, and then I go back down to having no sound in time. So you would essentially be hearing kind of like a wom 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 type of sound with a beat period. We can write the beat frequency as simply being the difference in these two sounds, so frequency 2 minus frequency 1, or 60 Hertz minus 50 Hertz, and we would get a beat frequency in this case of 10 Hertz, and we can relate that to the beat period simply by saying that the beat period is 1 divided by the frequency, and we can see that the beat period is going to be 1/10 of a second. Another interesting phenomenon that we can talk about is something called the Doppler Effect. We know that waves are going to travel at the speed of sound, which is going to be 343 meters per second for air. However, if we have an object that is moving, we also have to consider the speed of the object with respect to an observer. If we consider just a fire truck at rest and it's got a siren at a single frequency, I'll call that F, then it's emitting these wavefronts, these crests and troughs that are moving away from it, and a person over here is going to hear the frequency of the fire truck F, which is related to the speed of sound and the frequency of the fire truck. On the back side of the fire truck, then it's going to have these same wavefronts with the same frequency, and the person over here is going to hear the frequency, and all these frequencies are going to be the same. However, now if we consider a fire truck that is moving, it's going to be emitting some frequency, but now it's moving, and essentially the fire truck is catching up to its wavefront. It's driving towards them, and so the wavefronts are going to be compressed. So this person over here is going to hear these frequencies, and the wavefronts are closer together. On this side of the fire truck is essentially running away from the wavefronts, and so they're going to be further apart. So we're going to hear a different frequency, and in this case, this frequency 2 is going to be lower than the frequency 1. And you've probably observed this many times in your life and never really thought about it, but I could probably play a fire truck going past you and you could tell me when it was coming towards you and when it was going away from you. Now, it is of course fun to talk about it, but this is a physics class, we need to learn how to calculate it. So if I am right here and I'm standing there and I have a source coming towards me, now at point 1 this source is going to emit a wavefront, and this crest is going to be coming towards me just like that, and now a little bit later the source is going to emit another wavefront. However, now the source has moved, so here's the second wavefront. We know that the distance that the source has moved is related to its velocity multiplied by the time, and that's going to be related to this, or that's going to be the same as this lambda prime, this distance between the two wavefronts. We can figure out what this change in wavelength is by considering the distance between the two pulses. So this is going to be my first pulse and this is going to be my second pulse that's shifted now because the source has moved. So the distance that the first pulse has traveled is going to be the velocity of sound multiplied by the time, or the period of the wave. This second pulse right there was emitted at a slightly different distance. That's going to be the velocity of the source now multiplied by the period. So this is going to simply be the initial wavelength, and we can write this second distance as such. We can relate now the period to the wavelength and the velocity of sound, and we come up with our new wavelength as a function of the original wavelength and the velocity of the source relative to the velocity of sound. We can relate this change in wavelength to a change in frequency, recalling that frequency is going to be the velocity of sound divided by the wavelength, so this change in wavelength can be related to the change in frequency, and we can write our change in frequency now as being related to the velocity of the source and the velocity of sound. So this is going to be one of the major equations to use when we're talking about Doppler effects. And keep in mind that this is going to be a source moving towards a stationary observer. If the source is moving away from the stationary observer, we can go through a very similar derivation, and we can come up with the second major equation that we can use. I'll put a star next to that, and essentially you can see right here all we're doing is we're subtracting off the relative velocity of the source to the sound, and this we're adding them together. Essentially it's whether we're adding those two wavefronts together or subtracting them off. Again, keep in mind this is going to be a source moving away from the stationary observer, so this would essentially be behind the fire truck, and this would be toward the fire truck, and you can kind of see that the frequency would be increased in this case and decreased in this case. We're going to have a similar but slightly different effect if we consider a source that is not moving and an observer that is moving now. In this particular case, we're going to have the source emitting these wavefronts, these crests, that are going to be one wavelength apart, and it's going to be traveling at the speed of sound. Now we have an observer that is moving, and essentially they're going to be crashing into these wavefronts, and they're going to therefore observe a slightly different wavelength than the source emitted, and you would intuitively would say they're crashing into them, so it's going to be a higher frequency. We can go through much the same derivation where we add the wavefronts together. We're going to come up with a frequency shift, in this case for an observer moving towards the stationary source now, and an observer moving away from a stationary source now. You can see how it's related to the speed of the observer and the speed of sound, and essentially it's going to increase the observed frequency, that's the frequency prime if they're moving towards it, and lower the frequency if they're moving away from it. The difference between these is just that subtle difference, whether it's a positive sign or a negative sign, keeping in mind whether the observer is moving away from or towards a stationary source. We can also consider where the observer is moving and the in this case the object is moving, and example 12:16 is going to show you how you deal with the observer moving and the sound moving, and I'm going to work one of these in the worked problems, but beforehand make sure you take a look at example 12:16 and familiarize yourself with observer moving and the object moving. Lastly, let's consider Doppler shifts and say, well, what happens if the source is actually moving faster than the speed of sound? If we consider an object that is not moving and it's emitting sound, it's going to emit it essentially in all directions. So it's going to have wavefronts that looked like this picture right here. If the object is moving in that direction, then we're going to have the higher frequencies over here, Doppler shifted, and the lower frequencies over here. Where if the object is moving now at the speed of sound, then we're going to have Doppler shift such that all of the wavefronts are going to be piled up right here at the front of the aircraft, and actually, conceptually, that that's going to be regions of very high pressure, so you can actually see cloud formations in that region right there. And if the object is moving faster than the speed of sound, it's outrunning its wavefront crests, and so you can get a shock wave that comes off of the nose of an aircraft that's going faster than the speed of sound. It looks very similar to the waves that are produced by a boat that's going faster than the wave speed in the water. You can kind of see the bow wave going off here. It looks very similar to the shape of the shock waves coming off of the tail of an aircraft. Aircrafts that are exceeding the speed of sound are actually going to produce two shock waves, or at least two. You're going to get a shock wave right here from the front of the aircraft. You're going to get one here from the tail of the aircraft, and you're actually going to get some coming off of the wings of the aircraft. Anywhere where we can get a pile up of waves. So someone on the ground is going to hear first the nose of the aircraft. It's going to hear a sonic boom from that. It's going to hear a sonic boom from the wings. It's going to hear a sonic boom from the tail of the aircraft. So you can actually Google shockwave from aircraft and see some really cool images of this if you're interested. Lastly, let's talk about some applications of sound. For example, sonar. If I have an object that can emit a pulse, so here's going to be a transmitter, then I can emit this sound pulse, and this sound pulse is going to go through a medium. In the case of sonar, it's going to be going through water. It's going to travel through the water. It's going to bounce off of surfaces such as the ground, and we're going to get a wave that is reflected backwards. If I know what the speed of sound in water is, and I measure this two-way time, and I can figure out the distance to any surfaces under the ground, simply by saying distance is equal to velocity times time. So we can use sonar, we can use sound to figure out where objects are underwater, assuming that the velocity doesn't change very much. Similarly, we can use the same type of technique to look at the internal structure of the Earth, as well as in ultrasounds, as I'll talk about on the next slide. For ultrasounds, we're going to have a transducer which is going to produce waves. These waves are going to essentially echo off of every single surface that it comes across. We're going to be measuring echoed waves, and we're going to be measuring essentially the time, which is going to tell us the distance to where various surfaces are inside of a body. This amplitude is going to be related to the density of the two mediums that we're looking at, and we can essentially from this build a picture of where things are in the human body. And if we know, roughly what we're looking at, and we know these densities, we can figure out where things are in the human body and what we're looking at. So it's a very interesting application. Same type of thing for ultrasounds. We put a transducer on an abdomen and we send out pulses, and we can produce interesting pictures of babies. And actually, if we do it from a whole lot of angles, we can produce a 3D image of your baby and get a feeling for who it's going to look like before it even comes out of the womb. These are the summary slides, and I'll just page through them so you can jot down anything you'd like.